Hello everyone, welcome to Microwave Engineering lecture series. In this lecture, we will discuss about the loading of transmission lines. In last lecture series, we have discussed about the waveform distortions. So while discussing the waveform distortion, we have seen the distortionless lines. So in which for any ideal condition, so when we are transmitting the signal, they should not be have any distortion. That is, whatever the signal is transmitting, the same signal we have to get at the receiving end condition. That is the ideal distortionless line. For any ideal distortionless line condition, there is a formula of RC is equal to LG. This already we have discussed in last lecture series. So but in a practical condition, we won't get the distortionless lines. They'll be having the distortion. So that is nothing but with the resistance and conductance will be high and the inductance and capacitance will be very low. So in order to reduce this resistance and conductance, so we know that we get the resistance and conductance because we use the lumped components in between this transmission lines. This I will discuss why we are getting the lumped parameters. To satisfy this condition, we have to reduce this R by G conditions. So this R by, when this R by G condition is very high, that is, we'll have the bulk of wires, so that we cannot able to transfer the lot of powers, and it will be the very cost effective. So this when we increase this inductance, we have the poor insulator also, and because of this insulator we have the poor leakage of power, and there will be the line efficiency also very less. So this we have to reduce this R by G by increasing the inductance and decreasing the capacitance. If we reduce the capacitance, that is, the separation between the lines will be more, so that we will have the large amount of wire will be the carried out, and so that we require a large amount of tower and post, and it will be the very costlier. So that to make this capacitance to be ineffective, we have to use the lumped inductors with the at the specific regular interval. This is called as the loading of lines. There are the different methods of loading. There we have the two types of loading. One is continuous loading and another is a lumped loading. In continuous loading, we have the heavy side of loading. In lumped loading, we have the coil loading. So this in continuous loading, it is the process of increasing the inductance by placing this iron core or the magnetic tapes over the conductor line. So in this method, we increase the L by tapes of the magnetic material, as in we are increasing the by reducing the coil. That is like we have the magnetic material will be the high, that is of mu material having the high permeability, which is wound around the each conductor. So the increase in L is given by L is equal to mu divided by D by NT plus 1 into microhenry. So here we can see this, yeah, mu is nothing but the permeability of the surrounding material, and D is nothing but the diameter of the copper conductor, N is the number of layers, and T is the thickness per layer. The propagation constant of continuous loading in the cable. For any cable, we have seen the ideal characteristics of impedance line, which is equal to Z by Y. That is, Z impedance characteristic impedance condition is Z is equal to root of R plus J omega L divided by G plus J omega C. For this continuous loading thing, we make as a G as 0, so we get this term Y is equal to J omega C. And this we know the propagation constant is gamma is equal to root of YZ. That is, we get this two term and we multiply here thing, and this by resolving, this is the gentle simplified term. When we resolve this equation, by resolving this equation, we get the continuous loading time, that is nothing but sine of 1 by t into tan inverse of R by omega L. So this cos theta is equal to 1 by 2 R of omega into L. So this is the cos theta. So we know this. In after loading thing, we try to neglect this omega L condition. So always this inductance will be higher than the resistance condition. So here we can see this, we have find out this propagation constant alpha, that is attenuation constant, and phase constant as in beta term. In ideal condition, in last lecture series, we have seen this alpha should be the dependent on frequency, whereas beta should be the independent of frequency, and the propagation constant of velocity of propagation should be also independent of the frequency. So that we get alpha is equal to R by 2 into root of C by L. This is the ideal condition thing. So when we try to resolve this condition, we get the characteristics impedance Z0 is equal to root of Z by L. This actually we have to remember this equation for solving the remaining equation. So R plus j omega L divided by G plus j omega C. And here we know this for any characteristic line, we make this resistance and conductance should be very less. So this we make as in 0. So we get only the root of LC condition. So here is we'll discuss about the advantages and disadvantages of continuous loading. So already I have discussed for the any distortion lens line, we have the attenuation should be the independent of the frequency. For similarly the continuous loading also we have the attenuation should be independent of the frequency, so that when attenuation is increased by increasing the L, and this we will not disturb the resistance parameter. So maximum length of where we have to keep the inductance lumped parameter between the line is, so every 100 meter we'll use the 100 microhenry of line. For every 1 meter of length we use the 100 millihenry of unit length should be the possible thing. So what is the disadvantages? It is a very expensive because we are trying to increase the inductance at certain length. So when we try to increase the length line, if we go for the long distance communication, it is very difficult, and we cannot able to replace the inductance lines. Thanks for watching. In next lecture series, we'll discuss about the lump loading and the input impedance parameter.